This is a reading of Chapter 11, Section 1 on mountain formation. Section 1, where mountains form. A mountain is a large mass of rock that rises a great distance above its base. Most mountains result from forces associated with processes that occur at convergent plate boundaries. Remember, that's where two plates are coming together, one of them subducting under another. Mountain belts. Most of the world's mountains occur in long belts that tend to follow convergent plate boundaries. These mountain belts are regions where mountains are forming or have formed in the past. The North American Cordillera is a mountain belt that runs down the western side of North America from Alaska to Mexico. This mountain belt is made up of smaller groups of mountains called mountain ranges. For example, the Cascade Range is part of the North American Cordillera. Some mountains, such as the Himalayas, lie along current plate boundaries. Other mountains, such as the Appalachians, do not. By analyzing how the rocks in the Appalachians are arrayed, and by studying the ages of the rocks and the materials in them, geologists have concluded that the Appalachians formed at a plate boundary that existed millions of years ago. Continental margins. In order to understand how processes at convergent plate boundaries contribute to mountain building, geologists study what happens along Earth's continental margins. A continental margin is a boundary between continental crust and oceanic crust. There are two types of continental margins. Active continental margins occur along plate boundaries. Passive continental margins do not occur at plate boundaries. For example, there is an underwater continental margin along the east coast of North America that marks the boundary between the North American continent and the oceanic crust. Both the continental crust and the oceanic crust along this continental margin are part of the North American plate. Mountain building takes place near active continental margins. One place where an active continental margin exists along the west coast of South America. Here, the Nazca plate, which is carrying oceanic crust, is subducting beneath the South American plate, which is carrying continental crust. The west coast of South America is very mountainous and prone to earthquakes and volcanic activity. The slow process of mountain building is taking place today in this region. Passive continental margins are stable areas because they do not occur at plate boundaries. These areas accumulate large amounts of sediment. Some of the sediment comes from skeletons and shells of marine organisms, but much of it consists of sediments that have been weathered away from the continent and transported to the continental margin by rivers. One example of a passive continental margin lies off the east coast of North America. A wedge of sediment 250 kilometers wide and as much as 10 kilometers thick has accumulated there. Eroded rock materials from the Appalachians now lie along this passive continental margin. Sediment buildup at a passive continental margin. Over time, mountains wear away, creating sediments. Rivers and other agents of erosion carry sediments to the ocean, and these and other sediments are deposited along passive continental margins. How are passive continental margins related to mountain formation? These passive continental margins provide the materials that form mountains. The mountains of today were passive continental margins in the past. The active continental margin on the west coast of South America was a passive continental margin until about 200 million years ago. The Andes Mountains contain the sediments that were deposited on that passive continental margin. At this time, take out a sheet of paper and answer the three questions for this Chapter 11, Section 1 review. Chapter 11, Section 2. How mountains form. A sculptor uses a hammer to hit a chisel, and the point of the chisel hits a rock. The rock breaks because the sculptor has concentrated the force of the hammer blow onto the relatively small area where the chisel meets the rock. The sculptor has increased the amount of stress being applied to the rock. Stress is a measure of the amount of force applied over a given area. Stress is applied to rocks at converging plate boundaries. Rocks at Earth's surface are rigid and usually respond to stress by fracturing. Deeper in Earth, high pressure and temperature make rocks less rigid than those at the surface. For this reason, stress applied to rocks deep within the lithosphere may cause the rocks to fold or stretch without fracturing. Mountain belts are made of rocks that have been permanently deformed under stress. Types of stress. The illustration at the right models a series of rock layers. The bottom rock layers are under stress from the weight of layers above. Overall, however, the rock layers are relatively stable. The illustrations below show 3 different types of stress that might affect the rock layers. Compression. The rock layers are being squeezed inward. Stress that involves squeezing is called compression. Compression tends to make rock layers thicker and shorter. Tension. The rock layers are being stretched. Stress that involves pulling and stretching is called tension. Tension tends to make rocks thinner and longer. In this illustration, some of the rock layers have fractured. Shear stress. The rock layers are being pushed in 2 different opposite directions. Stress that involves forces moving in opposite directions is called shear stress. Shear stress tends to distort the shape of the rocks, especially along the plane between the opposing forces. Compression, tension, and shear stress all contribute to the process of mountain building at plate boundaries. These 3 types of stress usually occur together. Different types of rocks may respond differently to the same stress. For example, a layer of sandstone may respond to stress by folding. A thin layer of shale lying next to the sandstone may fracture rather than fold. Folds. During plate collisions, stress can cause rock layers along continental margins to crumple into folds. Although this folding occurs deep beneath Earth's surface, folded rock layers may be exposed after long periods of time by uplift, weathering, and erosion. Geologists use a number of terms to describe folds in rocks. As shown in the diagram below, an anticline is an upfold in the rock layers. A syncline is a downfold. The 2 sides of a fold are called limbs. The steepness or dip of the limbs reflects the intensity of folding. Limbs may be gently dipping, steeply dipping, straight up and down, or even overturned. The compass direction of the fold or of the rock layers exposed at the surface along the fold is called a strike. Sometimes folding can cause extreme deformation. In other cases, rock layers have been pushed into gentle anticlines and synclines. The easiest way to remember the difference between an anticline and a syncline is to remember that a syncline sinks. Illustrated here. This is a syncline where the rock has sunk or it sinks. An anticline is the opposite. You get an arc, opposite of a syncline. And of course, these areas is called a limb. This is a limb and a limb. A well-known example of folded mountains is the Valley and Ridge province of the Appalachian Mountains. In this region, which extends from New York State to Alabama, the rock layers have been badly crumpled. Instead of the stress of collision, has formed the layers into long, straight folds. Interestingly, the valleys between the mountains do not correspond to folds and inclines, nor the ridges to fold anticlines as one might expect. Instead, the locations of the valleys and ridges are controlled primarily by the weathering rates of the rocks in different areas of the folds. Faults. As you learned in Chapter 10, a fault is a break in a lithosphere along which movement has occurred. Not only are movements along fault planes the primary cause of earthquakes, they are also an important part of the process of mountain formation. The illustration at the right shows a fault plane, which is a surface between two pieces of moving crust at a fault. The part of the fault above the fault plane is called the hanging wall. The part of the fault below the fault plane is called the footwall. Geologists classify faults by the way in which the rocks on either side of the fault plane move with respect to each other. In each of the fault illustrations below, the large arrows indicate stress being applied to the rock. In each of the fault illustrations below, the large arrows indicate stress being applied to the rocks. The small black arrows show movement along the fault plane. A normal fault. A normal fault occurs when the hanging wall moves down with respect to the footwall. Normal faults occur in areas where tension is pulling the crust apart, as illustrated by these arrows. A reverse fault occurs when the hanging wall moves up with respect to the footwall. Reverse faults are caused by compression, as indicated by the arrows. Such compression may occur, for example, when two plates collide. The compression at a reverse fault thickens and shortens the rock. A thrust fault is a reverse fault, because you see that it's compressing, in which the fault plane dips 45 degrees or less from the horizontal. Thrust faults are common in many mountain belts, including the Appalachians. From studies of thrust faults, geologists have seen that compressive stresses can move sheets of rock over great distances. At a strike-slip fault, the rocks on opposite sides of the fault plane move horizontally past each other. The San Andreas Fault is a well-known example. Extremely long strike-slip faults are found in the Himalayas. These faults result as the Indian plate pushes rock materials aside on its drive into the Eurasian plate. Some of the faults are thousands of kilometers from the plate boundary. Joints. Joints, like faults, are breaks in bedrock. Unlike faults, joints are breaks along which no apparent movement has occurred. Joints can be the result of the same stresses that lift, tilt, and fold rock layers into mountains. They are one of the most common rock structures. The surface of a joint is usually a plane, although the surface of some joints are curved. The joint plane appears on the surface of a rock outcrop as a line. These lines can appear in parallel groups called joint sets. Sometimes one joint set is crossed at an angle by another joint set. Joints provide channels through which fluids enter and move through bedrock. Hot fluids rising through the crust may fill a joint with quartz, calcite, or some other mineral to form a vein deposit. Caverns form when groundwater flows through and dissolves limestone along joint planes. In some areas, surface features are controlled by joint patterns. The spires at Bryce Canyon are the result of weathering along joints. At this time, I want you to answer the Section 2 review questions, 1 through 7.